My name is Thi Tuyen Ngo. I'm from Multifunctional Material Group of Material Science Institute of Sweden. Some months ago, when I read about the event of European Research Night, I was very excited. It's a great opportunity to bring science to everyone. And I would like to thank the organizers of the event to give me the chance to bring our research to everyone. And today, I'm going to show you not only colorful light emissions from very tiny particles, but also why they're very important, why we do research on those particles. Before I show you our research, I would like to show you the locations of our institutes. So at any time, if you would like to visit us, you know where we are. I mentioned before, our institute is located in Sweden, the south of Spain. And concretely, is located in Colourful of Sweden. This is the main entrance of our institute. Our group is situated on the ground floors of the buildings in front of the main entrance. You can visit us at any time. It's always a pleasure for us to have your visit. This is our group. I would like to thank all group members, especially Professor Hernán Miguel, Dr. Gabriel Lozano, Dr. Jose Miranda, Elena Caballos, and Dr. Juan Galesteros. They mainly contribute to the work that I'm going to present. I would like to thank also European Research Councils, Junta de Andalucía, Fundación Geran C6, and Spanish ministries for the financial support. We're surrounded by so many light-emitting products. I'm sure that you're very familiar with a Christmas tree, which is decorated by many color lights, or you can find many decorative lights here on the streets on special days like New Year's or festivals. Moreover, light-emitting products appear in our life in every single day. For example, luminescent toys. They're very useful for children to play and to discover their own world. Another very important light-emitting product is a bulb. That's what we use to illuminate houses, offices, and buildings, etc. It has to be less dependent on sunlight. Or in other words, it has to be less dependent on nature. So we have seen that light-emitting products are very important. They have to improve the quality of our life. So what we do at the Institute of Materials, we prepare materials, we emit strongly light with different colors. And those materials are prepared from very tiny particles that I'm going to show you later. We know that a bulb will not shine without connecting to electricity. Our car cannot run without providing a fuel source. Another thing is even more simple. In order to sustain life, we need to provide nutrition to our bodies. Similarly, in order to have emitted light, we need to provide something to our materials. In this case, we decided to expose our materials under a light source. However, what a light? We know that when we stand under the sun, we feel hot. So it means that sunlight has energies. Our body just absorbs the energies from the sunlight and convert it to thermal energy. That's why we feel hot. So when we expose our material under light source, the material absorbs the energies from the light to be excited and emit light. You may wonder why we decided to give a light to our material to have another light. The reason is not every light has the same energy. We expose our materials under a light source with one energy to have emitted light with another energy. Sunlight is an example of very complete light source. It's composed of many photons, and each photon has different energies. The energies of a photon increase when going from infrared to visible and ultraviolet light. It's very important to mark that human eyes can see very short range of sunlight, which is marked here as visible. And we are blind with ultraviolet and infrared light. So at the institute, we use infrared or ultraviolet light to excite our samples, depending on the materials, in order to have emitted light in the visible range. Here I show you some examples of yttrium oxide fluoride doped with lanthanide samples that we prepared in our laboratory. You can see that before exciting, they don't give any emissions. However, under the illuminations of infrared light, the materials will absorb the energies of infrared light and give red and orange emissions. In this case, the emission has higher energy than the excitations. This process is called upconversion. Here I show you how the emission spectra looks like in the detectors. Our group also prepared materials which absorb the energies from ultraviolet light to give the emissions in the visible. In this case, the energies of the emissions is lower than energies of excitations. This process is called dark conversion. Important to know that our samples are highly transparent and flexible. This is very important for the applications, as flexible coatings can be easily placed on any kind of objects with different shape. In the coating preparations, if you put patterns, you can generate very nice images. Or you can merge different emission light color to generate a new one by combining different types of particles. There are samples before exciting. They were transparent. We cannot find any trace of particles. This gives rise to the applications of anti-counterfeiting. For example, a layer of phosphor particles were deposited on money. Under daylight, we don't see those particles. However, under ultraviolet light, the particles will absorb the energies of ultraviolet light and give green and red emissions. This has to be not confused with counterfeit monies. The particles can be used to prepare anti-counterfeiting stamps, then based on any kind of products. On the gift, for examples, here we see the importance to have flexible coatings as we adapt the shape of the product. The samples I have shown you actually is prepared from very tiny particles. When I say tiny, I mean the size of the particles are very small. This size is in the range of nanometers, which is 5 order of magnitudes lower than the size of your hair. The particle size and the layer thickness can be easily tuned. The synthesis of particles is very simple. We put on precursors in a tube and heat them. After some time, crystals are formed. And when we continue heating the solution for longer, they're growing and forming particles. Here I show you how particles look like after the synthesis. We can use directly this particle suspension to prepare thin films. We drop some suspensions on the substrate and spinning to have the thin films. We also heat these samples to crystallize particles. In order to have thick films, we prepare paste of particles by evaporating the solvents of particle suspensions. Then we pour a paste on substrate and expand it on the surface to have the coatings. We also heat the samples to crystallize particles. The emissions measurement is very simple. We use a laser to excite our samples with an invisible light. The emitted light is collected by a detector, which is connected to a computer. The emission spectrum is displayed on the computer screen. Important to note that the particles emit strongly not only in a solid state, but also in a liquid phase. Having high emissions in the liquid phase is one key parameter for the particle to be applied in biology. As mentioned before, the particles can be excited under the illuminations of infrared light, which has low energies. The advantage of low excitation energies is less damage for the samples during the measurement. This is another important case permit the particle to be applied in biology. Moreover, particles exhibit good brightness and uninterrupted emissions, which allows a long-term tracking for biomolecules. For complex systems like proteins, it's very important to visualize and distinguish different parts of the system at the same time. So the possibilities of tuning the emission colors of the particles is very suitable for multiple targets of biological imaging. The phosphor particles can be applied in medical examination and treatment. For instance, the phosphor particle can be conjugated with drug molecules. These drug molecules are targeted to reach the tumors. The combination then injected in vivo animals, and under the illumination of infrared light, the particles will absorb the energies of infrared light to give the emissions in the visible. Now the emissions is clearly seen by the human eyes. Phosphor particles are linked with drug molecules, so the positions of the phosphor particles are also the positions of drug molecules. And as drug molecules are targeted to reach tumors, so the positions of these combinations are also the positions of tumors. Therefore, by linking phosphor particles to drug molecules, the tumors can be clearly visualized, and their size can be estimated precisely. Phosphor particles can be used for testing new drugs as well, as they visualize the path of injected molecules in vivo animals. This permits biologists to estimate how efficiently the new drug can reach to the target part of animals. You may hear about fiber optics, or even you are using them to connect internet, where you can find so many informations. Fiber optics are actually a waveguide, which is used to transfer information in light signals from one point to the other. Light signal is preserved and transferred quickly due to the total internal reflections. This kind of waveguide is very important. It's able to send information in very short times. You can find the waveguides in decorative products as well. The products are available in commercials, and you can easily buy them. The phosphor particles can be applied to prepare waveguides as well. They are dissolved in a polymer to obtain highly viscous solutions. And by printing the solutions, polymer waveguides can be obtained. They are very stable. They emit strongly under bending and rolling conditions. And we know that phosphor particles can convert invisible light to visible light, so they can be used as a photodetector. This is very useful for researchers to build optical setups for the measurement. Moreover, invisible light can be converted to electrical signals as well. This permits to record and to quantify the amount of invisible light. You're very familiar with solar panels, which are used to generate electricity from sunlight. And these solar panels has many solar cells connected to each other. And these solar cells compose of unabsorbable materials. Under illumination of sunlight, these layers will absorb the energies of the sun and generate negative and positive charge. We can connect those charges in an external rod to use them. However, the solar cells can convert sunlight to electricity, depending quite a lot on how much these layers can absorb the energy from the sunlight. Many investigations have been done in order to improve the efficiencies of solar cells. However, up to date, solar cells don't convert efficiently infrared light into electricity. And we know that photoparticles can absorb the energies of infrared. So adding the photoparticles in the solar cells can help to improve the efficiencies of solar cells. Here I show you some examples of adding photoparticles in solar cells. We see that when we add the photoparticles, the photocurrent and photovoltaics are increased. Another very important application of photoparticles is lighting. When I say lighting, I mean white light. That's the light we use to illuminate houses, offices, buildings, etc. This is a schematic view of a white light bulb. It's constituted of light-emitting diodes, which emit a blue light. This light-emitting diode is covered by layers of photoparticles. The photoparticles will absorb partly a blue light to keep the emission in yellow light. The combinations of yellow and blue lights will give us a white light. We have seen that the photoparticles are very important. They can be applied in many different fields. So what we do at the Institute of Materials, we're enhancing the emission intensities and tuning the emission color. For instance, I will combine two different types of photoparticles, in which one has a blue and yellow emissions, the other one has a red emissions. By adjusting the intensity ratios of those emissions, we can generate a white light. We're also focusing on the optimizations of structural properties of the particles in order to maximize the emission intensities. If you look at the sky, you can see that clouds are white. Clouds are actually made of many tiny droplets of water. When sunlight with different colors hit the droplets, they scatter in all directions. So the combination of different colors of scattered light will give us the white light. Those droplets of water are actually scattering centers. They scatter light in a random way. So in our group, we also introduce scattering center in the system, but in the controlled ways, in order to enhance the intensities of photoparticles. For instance, titanium oxide microspheres are added in the layers of photoparticles. And the illumination, the microsphere will scatter the excitation light, enhancing the time for excitation light traveling inside the layers. This increases the possibilities for excitation light to be absorbed, then enhancing the absorption emissions. The photos confirm clearly the introduction of scattering centers can enhance clearly the emission densities of photoparticles. If you put a candle between two mirrors, you can see infinity candles. They are actually the images of candles due to the fact that light is reflected from one mirror to the others. The interesting thing is, by reflecting many times between two mirrors, the intensity of light is enhanced quite a lot. And this actually is the working principles of laser cavities. Our group also prepared very similar systems to enhance the emission intensities of photoparticles. You may see butterflies many times in your life, and they have so many different colors. The color of butterflies or any other objects that you see is actually the colors of reflected light. You may not realize that a wing of any butterfly is composed of the same materials. This is the structural view of butterfly wing. It has so many layers. Changing the size of the components in these structures will change how the light reflected on the butterfly wings. This causes the change in the colors that we observe. A butterfly wings is the clearest example of photonic structures. We can tune the reflected light. Our group also prepares a photonic system to tune the reflected and emitted light. Similar to the butterfly wings, changing the thickness of any layers in this system will change the reflected light. The changing now is visualized by a black curve in these figures. Due to the change in the reflected light, we observe different colors. The phosphor particles that we incorporate in the systems had two emissions, blue and yellows. Changing the thickness of this system also causes a change in the ratios of intensity of those emissions, which is visualized by the red curve. Due to the change in the ratios intensities of the emissions, we observe different colors in the emissions. In summary, I have showed you that phosphor particles can be easily synthesized. They emit strongly different colors in both solid and liquid states. And such kind of particles have many applications in anti-counterfeiting, biology, lighting, etc. I also show you our approaches to enhance the emission densities and to tune the emission colors of phosphor particles. Thank you very much for your attention. I hope you enjoy it. On the works I have present, I belong to Nanoform, that is an European research project on phosphor particles for lighting applications. This is the webpage of the project. Please visit this webpage to have more detailed information. I would like to remind you that we have a chat section after the presentations. So if you'd like to discuss or to ask questions, please join the chat. You also have my email address, so you can write to me if you have any questions. This is the webpage of our group. All the research lists and activities are described there, so please have a look. Thank you very much again, and see you in the chat.